Alright, in this video we're going to kind of look at an addendum to the previous objective where we were trying to estimate area under a curve. There are a few curves that we can actually find the exact area under the curve if we just appeal to the geometry of the function. So if we're looking at example 1, it says find the integral from -1 to 1 of the quantity 1 minus the square root of 1 minus t squared with respect to t using geometry in the graph below. So that whole find the integral from -1 to 1 just means we want to find the exact area from here to here under this curve. So we want to find the exact area of all of this stuff here and the exact area of all of this stuff here. Now we could, if we wanted to, use Riemann sums like we did in the previous video. But what we're going to want to do here instead is we can see by looking at this, we have a rectangle. Right? We see a rectangle here. We can find the area of that rectangle. We know it's going to be base times height, so base is going to be 2. And the height's 1, so we know the area of the entire rectangle is 2. Now, we don't want the area of the entire rectangle. We want just the area of that red part. So if we take the area of the entire rectangle and we subtract out the area here that I'm kind of coloring in green, we can get the area of the red spot. So the area of the green, well, that's just a semicircle. So the semicircle, the area of a semicircle is pi r squared over 2, right, divided by 2 because it's only half the semicircle. So pi r squared, well, r here is just 1, so 1 squared is 1 divided by 2. So pi r squared over 2 is just going to be pi over 2 for that semicircle, so then we can figure out the area that we're asked for, so we'll just say the area of the red is going to be the area of the rectangle minus the area of the semicircle. So that is the exact area of that red section. Something else that we can deal with is if we are given a graph and they tell us what a certain area is. So if you look, they're telling us it's a fact that we're actually going to figure out later. We don't know right now, so you're just going to have to take my word for it. But it's a fact that the integral from 0 to 2 of sine of x dx, from 0 to pi, of sine of x dx equals 2. Use this knowledge to find the following integrals, and I've given you a graph of y equals sine of x from negative pi to pi. So they're telling us that this shaded region here has an area of 2. There's a couple of weird things that are going to happen as far as what we're talking about with area. So if we look at 1, they want the integral from pi to 2 pi. So if we were to extend this graph, here's pi, we go like this and get to 2 pi. So we'd have this area down here below the x-axis. So knowing that the graph of sine is symmetric, we would know that this stuff has an area of 2. So the integral from pi to 2 pi of sine of x dx, we would think is 2. But here's where things get a little weird. Since we are below the x-axis, this area is not going to be 2, it's going to be -2. So that seems a little weird because we usually don't have such thing as negative area. But if you think about what an integral means from the last video, remember that it's the total change in whatever the antiderivative was. So if we're talking about a velocity graph and this area, or the y values here, represent miles per hour, well, we have a total change of -2 miles, which just means we went backwards 2 miles. So a negative area in and of itself doesn't make sense, but if we attach some units to it, it should make a little bit more sense. So that's the first weird thing that can happen. The other two weird things are going to come up when we get to 4 and 5. So I want you to pause the video right now, take a second and try to answer 2 and 3. Alright, so let's see how well you did. For 2, we want the integral from 0 to 2 pi of sine of x dx. So here's 0 to pi. Remember, 2 pi would go like this. So we'd have this area here. We talked about this area here being negative. These are symmetric, so we should have gotten an area of 0. Looking at number 3, the integral from 0 to pi over 2 of sine of x dx. So it's only going to be half of this, right? If this here is pi, here's pi over 2. These pieces are symmetric, so if this whole thing is 2, that should be 1. So hopefully you did well on those two. Let's look at number 4. One of the things, and we're going to talk about this in more detail later, I just kind of wanted to show you this because it's going to show up on one of your assignment problems. But one of the things that we're allowed to do with integrals is if we have addition or subtraction in the problem, we're allowed to break this up into 2 separate intervals. And again, we're going to talk about this stuff a lot more once we learn to take these integrals by hand. But this is something I want you to keep in mind for when you go to do your assignment. So if there's a plus or minus in here, we're allowed to break it apart. So that makes this problem a lot easier because we know from the given that this has an area of 2. And if we think about what this means, it means the area under the curve from 0 to pi. Well, the curve here is just y equals 2. So if we were to look at a graph of y equals 2 from 0 to pi, it's going to look like a horizontal line. Well, when we find the area under that curve, it's just a rectangle with base of pi and a height of 2. So we know this is going to be 2 pi. So this total area is going to be 2 pi plus 2. So that's one of the little tricks that we're going to I'll use later, but I kind of wanted to show you because it's going to be in your assignment. When you have plus or minus, you can split this apart and then take advantage of the fact that you know what the graph of y equals 2 looks like. You can find the area under that easily because it's just a rectangle. Alright, number 7. Another thing that we're going to talk about later shows up in this one as well. So we have 0 to pi of 2 sine of x with respect to x. If we have a multiplication by a constant, and again, we're going to talk more about this later, but you need these little tricks for your assignment. We can pull the constant, and only the constant, out front. So we can really say 2 times the integral from 0 to pi of sine of x dx. Well, we know that is 2, so we're looking at 2 times 2. So this answer is going to be 4. Again, you can only do this with a constant. So if you had something like 0 to pi of x sine of x dx, you cannot pull the x out front and make it x times the integral from 0 to pi of sine of x dx. Only when you have a constant. So again, I want you to pause the video real quick, see if you can figure out number 6. Alright, let's see if you guys came up with the correct answer. So this one's a little bit different than number 4. In this case, the x minus 2 is within the function. So we cannot rewrite this as the integral from 2 to pi plus 2 of sine of x minus the integral from 2 to pi plus 2 of 2. So since it's inside the function, we're not allowed to do that, only when it's outside. So we got to think about, what does sine of x minus 2 look like? Well, it's going to be the sine of x just shifted to the right 2 units. So it's going to have the same exact looking graph, except it's going to be shifted over 2. So really, you're intersecting the axis here. So you're looking, like this. So then we got to think, what does this 2 and this pi plus 2, what do those do when compared to our original problem up here? Well, 2 is 2 units to the right of 0. Pi plus 2 is 2 units to the right of pi. So when I shifted my graph right 2 units, I also shifted what I'm calling my limits of integration right 2 units. So this graph should end up having the same exact area because everything has been shifted to the right 2 spots. So that'll do it for this video. We will see you in the next one.